Okay, so this is a video as far as an introduction goes to ionization energies of the elements. Okay, now we're not talking about making general ions that you're used to. Okay, so we're not making chloride ions or magnesium ions or anything like that. There is a definition of an ionization energy, and it holds true for all the elements. Okay, it's actually known as the first standard molar ionization energy. I'm going to use IE. So if you see capital I, capital E, that's ionization energy. Okay, and the definition is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. Okay, so that's on your worksheet. Your definition's there. So it's the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. That definition is massively important, okay? And there are units to this because we are talking energy, so it's actually kilojoules per mole, okay? So you'll see these values listed as kilojoules per mole to remove 1 mole of electrons from 1 mole of gaseous atoms, okay? There is a general equation that goes with these ionization energies, and it is as follows. So we're going to use element X. That's any element that you choose to have a go at. Now, the states of matter really important because that's part of our definition of gaseous atoms. So it's any element that's a gas, and it's the energy required to remove 1 mole of electrons to form the ions. And because we're removing an electron, every single element, doesn't matter what it is, forms X plus. And of course, we've removed this electron, okay? Like so. So this is your general equation for the first standard molar ionization energy for any element. So you can put anything you like in there. For example, silicon. So silicon gas goes to Si plus gas and an electron, okay? There are a second and third molar ionization energies, but we'll come across those in a later video termed succession ionization energies, okay, or successive ionization energies, where we remove more than 1 electron. But for now, we're just focused on the first one. So the amount of energy required to remove this electron is different for each element, okay? So when you have a look, there's a graph, okay, which you can download of the first 20 elements and how their different ionization energies look in terms of a trend, okay? So each element has a different first ionization energy in terms of the energy it takes to do so, okay? There are 4 really important factors that affect that, okay? So the factors that influence first ionization energy, or all ionization energies really, okay? So these factors actually dictate how easy or how difficult it is to remove this electron, and hence how much energy it requires. So the first one, and one that's probably one of the most important ones, is the actual charge on the nucleus. Now, as you would expect, the greater the charge in the nucleus, the more protons it has, the more difficult it is to remove that electron, because the attraction is actually greater. So the greater the charge in the nucleus, the more difficult it is to remove that electron. The second factor is something we call shielding. Now, shielding talks about how many energy levels of electrons are in between the nucleus and the outer electron. So what we've got is our nucleus, there's our first energy level, our second energy level, and so on and so forth. The greater the number of energy levels in between the outer electron and the nucleus, the easier it is to remove that electron. They interfere with sorry, that's the dog in the background, by the way, that interfere with the attraction between this electron you're trying to remove and the nucleus, okay? So shielding plays a massive part in finding out what the ionization is, or explaining what the ionization energies are. Third factor is distance from the nucleus. Okay, so the further away an electron is, the easier it is to remove. Kind of goes hand in hand with shielding, really. Okay, but it's always worth mentioning this as well. And I'm going to put number 4 in a bracket down here because you should only ever talk about this when these can't explain, because there are some exceptions to the rule. So number 4 is, does it have a half full or full outer orbital? Because as we said in a previous video, when we looked at electronic structure, they are more stable when they have a half full or full outer orbital. Now these only play a part in 4 exceptions that you need to know about. So you should never reference this and if these 3 can explain the difference between 2 ionization energies in terms of elements. Okay, so you need to use these to explain it. If they can't explain it, this must be the thing to explain your exceptions. Okay, and they are basically the difference between beryllium and boron, nitrogen and oxygen, magnesium and aluminium, and phosphorus and sulfur. These are your exceptions, but I'll go into these in more detail in a later video. So the next 2 are going to be talking about the trend in ionization energies down a group and the trend in ionization energies across a period, and how we can use these, the balance of these, to explain the difference in ionization energies. So know your definition. You must be able to write an equation and know the 4 or 3 major factors that influence ionization energy, and the 4th there that we can use to explain these 4 exceptions.